Hi everyone. In this video, I'm going to be taking you through how the DJI digital FPV system works from a technical perspective. This is the second in a series of videos that I've been doing on FPV video systems. I've already covered analog video, and I'm going to be covering the SharkBite or HD0 digital video system in a little while. So make sure you subscribe and hit the notification bell so you don't miss that video when it comes out. There's lots to cover, so let's not waste any more time. Let's get right into it. First, I want to summarize the whole process that takes you from an image falling on your camera all the way through to a digital wireless data transmission between the air unit and your goggles for the DJI HD FPV system. So first, an image falls onto a CMOS sensor, and this sensor converts those photons of light into a raw digital image, which is passed to an image signal processing chip. This is a specialized chip that's designed to improve the quality of the image and make it as good as it possibly can be before transmission. That improved image is sent digitally to the air unit over the wire, and the air unit conducts digital video compression and encoding on that image before transmitting it wirelessly to your goggles. We're going to go through this whole process step by step, and I'm going to explain how each of these stages is done. Firstly, the sensor in the camera converts photons of light into electrical charge. This analog signal is sampled by an analog to digital converter, or ADC, within the sensor to create a digital representation of every pixel in the image. This raw digital image is then passed to an image signal processing chip, which performs things such as sharpening, wide dynamic range, white balance, and more, all to improve the image quality. This improved image is then sent to the VTX over a digital interface called MIPI CSI. MIPI CSI stands for Mobile Industry Processor Interface Camera Serial Interface, and it's just a standard. It's an agreed standard for digital image transmission. Now, the data rates for uncompressed digital video are huge. If we look at 720p at 60 frames a second, we see that that's 1.32 gigabits per second of data that has to be transmitted. And if we look at 720p at 120 frames per second, it's twice, it's 2.64 gigabits per second. So the MIPI CSI interface uses up to 4 data lanes in parallel, and each data lane runs at 1 gigabit per second. So it's really fast. In fact, the bandwidth between your camera and the VTX is most likely much higher than your internet connection or anything like that. Here you can see a schematic of how the interface works. So you have a clock lane, which is used to synchronize the electronics on either side of the connection. And then you have 4 data lanes, and each of these data lanes consists of 2 wires. And the reason there are 2 wires is because it's a differential signal. So when the signal on one wire is high, the signal on the other wire is low, and vice versa. And by always having one wire high and one wire low, and just switching which wire is high and which wire is low, you can actually get a signal that is more robust to noise. And with those 4 data lanes, you can get up to 4 gigabits per second. The MIPI CSI data rate, as we said, is around 2.64 gigabits per second for 720p at 120 frames a second. And the wireless link from the air unit to your goggles is either 24 megabits per second or 50 megabits per second, depending on which mode you have it set in, and reduces as you fly further away. So you can see that we need to reduce the data rate by a huge amount. We need to reduce it by 52.8 to 1 in order to squeeze it into 50 megabits, or 110 to 1 for 24 megabits. This is done through a process called video encoding and compression. You might be familiar with video compression on YouTube, for example, where the quality of the video is reduced if your internet bandwidth is less. And it's exactly the same process. You can see here that we can take an image, compress it a bit, and we don't notice much difference. If we compress it even more, then we can start to notice the difference. And the trick is to try and get enough compression without damaging the image quality too much. Now, DJI's compression methodology is proprietary, but we can still discuss the main elements of H.264 video compression as an example, because we can be pretty confident that DJI is using at least some of the same techniques. Now, video compression typically uses 3 techniques to reduce the data rate: prediction, residual transformation, and quantization. And we're going to go through each of these 3 techniques in turn. Let's first talk about prediction. So first, a single frame of video is broken up into macro blocks of 16 by 16 pixels. Each macro block can then be broken up into up to 16 blocks of 4 by 4 pixels. And it will depend on the complexity of the image how many blocks each section of the image is broken up into. But you can see the schematic here that shows how blocks can be broken up. Intra prediction tries to predict the contents of a block based on other previously encoded neighboring blocks. So for example, if we have this yellow block here, we might be able to predict what it would look like based on what this block and this block look like. Interprediction tries to form a good prediction of a block based on parts of previous frames. And this works really well for slow movement, where one part of the frame might be the same as another part of a previous frame. So let's look at intra-frame prediction in a bit more detail. Now, each block of an image can be predicted based on the blocks above and to the left of it in the frame. And when a video frame is encoded, it starts with the top left block, moves across to the top right block, and then goes down line by line from left to right, just like, reading a paragraph of text. And that means that if you've got a block in the middle of the image, you know that you'll have blocks above that you've already encoded and a block to the left that you've already encoded. So you can use these blocks to predict what that block should look like. And there are 9 different intra-prediction modes. And that sounds like a lot, but actually it's all just averaging. So we're going to go through them one by one. The first thing to know is that we're only using the bottom row of pixels from the blocks above. And we're going to call each of those pixels A, B, C, D, and then E, F, G, H. And we're only using the rightmost pixels from the block to the left, which we're going to call I, J, K, and L. So there's only 12 pixels that we're using to do the prediction. In the vertical mode, we just take the pixels above the block and project them down in columns, making each column the same as the pixel above it. And in the horizontal mode, it's exactly the same. We take the pixel to the left and project it across as a row, and every pixel in the row is the same as the pixel to the left. The third mode is the DC mode, and in that mode we just average A, B, C, D, I, J, K, and L together, and we make the whole block that color. The remaining prediction modes are a little bit more complicated. In these modes, we average together pairs of pixels, A and B, B and C, C and D, etc. And then we project that average in a particular direction. So if the projection arrow ends in unencoded space, we simply take the average color at the tail of the arrow and project it all the way along the arrow. If the arrow ends in encoded space, where we do know what the color is, we do a linear fit along the arrow between the color at the tail of the arrow and the color at the head of the arrow. It's just a linear fit between those two. And looking at all those different directions, that gives us all our prediction modes. Now, as well as intra-prediction, there's also inter-prediction, which is called motion compensation. Now, each block can be given a motion vector that indicates where that part of the image will end up in the next frame. So if you've got a smooth panning shot, for example, all the blocks will get a motion vector that says just move to the right by a bit. If a motion vector is not provided for a particular block, it can still be predicted based on the motion vectors of neighboring blocks during the decoding process. So this schematic shows how it works. So we have a 4x4 block in our current frame, and we're looking to encode the next frame. And we see that this 4x4 block moves up and to the right in the next frame. And so we can predict where it will end up with this motion vector, and we can then encode the next frame by saying, we'll just take this block and move it a bit, and that will give you the block in the next frame. Now, all of these different methods of prediction are compared, and the best prediction is selected based on the sum of the absolute errors. So whichever prediction is closest to the real image is what's selected. Now, once you have your best prediction for a particular block, whether it's an intra-frame prediction from some neighboring blocks, or whether it's based on a previous frame, you can subtract that best prediction from the real block, and that will leave what's called a residual. And the residual is basically the error in your prediction. You can describe this residual as a combination of basis patterns. And this process is called discrete cosine transformation. It sounds very complicated, but actually it's not really that complicated. You have these 16 patterns, and you work out for your residual block how much of each pattern you need to add together in order to get that block. And what you find by doing this process is that for most blocks, most of the time, it's only going to be 1 or 2 or 3 patterns that are really important, and the rest of the patterns will be negligible. And that allows you to reduce the amount of data that you need to send, because you can discard the patterns that are not important for a particular block and just transmit the parts that are important. The final process to reduce the data rate is quantization. Now, quantization is basically using rounding to reduce the number of bits that you need to send for each value, each pixel. So motion vectors for the interprediction that we talked about are usually quantized to 1, a half, or a quarter pixel levels, depending on the encoding settings. And the residual coefficients are also quantized, which helps reduce data. And any of those basis patterns that are not important, that reduce down to 0, are discarded. And all of this process helps save an enormous amount of data and gets us from our 2 gigabits a second of uncompressed video down to 24 or 50 megabits per second that we can transmit over the wireless link. And this diagram here just shows how you can do quantization in binary. You just add a half and then truncate the number, and you can see that we can effectively halve here the number of bits that we have to send over our wireless link by doing that rounding and truncation. It's worth mentioning at this stage that Luma and Chroma data is treated differently. So Luma is the brightness data for each pixel, and Chroma is the color data for each pixel. So you can see that if you just have the Luma data, you get a black and white image. And if you just have the Chroma data, you get this sort of strange, abstract, colorful image. Chroma is typically encoded at a lower resolution than Luma, so usually a half or 1/4 of the resolution. And this is done to save data because our eyes are much less sensitive to color than they are to brightness. So you can reduce the quantity of color data you send without the image looking noticeably worse. Once you have encoded and compressed the video data, you now have a small enough amount of data that you can transmit it over the wireless link. Now, this transmission is done using a scheme called orthogonal frequency division multiplexing, or OFDM for short. And the data rate for this type of link varies depending on the signal to noise ratio, the amount of interference that there is. And that means that the encoder settings and the compression settings for the video are always changing to match the amount of compression of the video to the available data rate. So as you fly further away and the available data rate reduces, the video is going to be compressed more. And that's why you see that the image goes blocky in your DJI goggles when you go far away, because there's more compression going on. Unlike an analog video signal, which uses a single carrier wave for the video, OFDM uses a huge number of closely spaced carrier waves per channel that we're going to call lanes. Now, 64 lanes or carrier waves is a typical number for an OFDM link. And each of those carrier waves is at a slightly different frequency, and they are all transmitting and receiving data in parallel. So you can kind of think of it like this. An analog signal just uses a single carrier wave, and that's like having a single wire, if you like, between your transmitter and receiver. OFDM uses lots of carrier waves in parallel close together, and that's like a bunch of wires bundled up. To minimize interference between all of these carrier waves, because they're very closely spaced, they have to be spaced at precise multiples of the symbol frequency or baud rate. So if you transmit 1,000 symbols per second, or 1 kilobaud, then you have to space each carrier wave 1,000 hertz apart. And similarly, if you were to transmit 50,000 symbols per second, you would need to space each carrier wave 50,000 hertz apart. Now, in most links, not all the carriers are used to transmit data. So in a standard Wi-Fi link, only 48 out of the 64 carriers are used for data. And each of the individual lanes is 312.5 kilohertz wide. Because of overheads, each of these 48 data lanes can transmit 250,000 symbols per second, and that's because there's always some overhead. And this diagram shows how the 64 lanes in a typical wireless link are set up. So you have these guard carriers at either side. They're not used to transmit data, they're just used to protect the link from neighboring channels. If there's interference because of a neighboring channel, it tends to happen on these guard carriers and it doesn't cause a problem. You also have a few pilot carriers, and these communicate data that helps maintain the link and assess how the link is doing, whether you might need to reduce the data rate of the link, for example. There's a DC carrier in the center, and this helps the receiver to lock on to the right frequency. And all of the rest of the carriers are used to transmit data. Now, each symbol on a data carrier can represent either just a single bit or multiple bits, depending on the modulation scheme. And this will become important later because we'll see that different systems use different modulation schemes. Now, in BPSK modulation, the amplitude of the signal is positive for 1 and negative for 0. So this is the simplest type of modulation. This is a 1 with a positive amplitude, and then 0 is exactly the same but flipped upside down. There's another more complicated type of modulation called QPSK, where you add 2 more states. And they're just the first 2 states, but they're shifted by 90 degrees. And you can see a diagram here showing the first and second ones, which are the same as BPSK, but then the third and fourth, which are just the first 2 shifted by 90 degrees. More complex modulations are possible, but you get the idea. You can represent more than 1 bit with each symbol. Based on the available information, we know that DJI is using a 20 megahertz channel in 24 megabit mode. And They may have split the channel into 64 lanes and be using 48 lanes for data, the same as Wi-Fi. And each of these lanes may be using QPSK modulation, and that would allow them to achieve a total maximum data rate for all of the lanes together of 24 megabits, which is what we know they achieve. In 50 megabit mode, DJI are using a 40 megahertz wide channel. Now, this might be split into 128 lanes, of which 100 are being used for data, again if they're doing something similar to what Wi-Fi does. Each of these lanes may be using QPSK modulation, and that would allow them to achieve a total maximum data rate of 50 megabits per second, which is what we know they achieve. Now, every wireless link is subject to interference. Digital data is transmitted as packets over the wireless link, and each packet is given a checksum, which is a small amount of data that can be used to check that the packet has been received without errors. Because of the type of video encoding and compression that DJI is using, all of the data is required to reconstruct each frame. You can't lose any of it, which means that if a checksum fails for a particular packet, the receiver requests a retransmission of the bad packet. And that retransmission hopefully gets through okay, and then the goggle is able to reconstruct the full image. These retransmissions add extra latency into the system that cannot be avoided. And because the number of retransmissions is variable, depending on how many packets are damaged during transmission, so is the latency. And the latency is likely to increase as the interference increases, because if you lose more packets, you'll need to do more retransmissions, and that just takes more time. In the DJI goggles, a similar process is happening in reverse to convert the digital data that's being transmitted wirelessly back into digital video that you can then see. So firstly, the radio link is demodulated to recover the digital data that's encoded within it. Once all the data for a frame has been received, that video frame can be decoded based on the data that's been transmitted and the data from previous frames. Then the uncompressed digital video is passed to the display, which creates the image that you see. So to summarize the advantages and disadvantages of DJI's approach here, using video compression allows a lot more visual information to be sent over the same bandwidth compared to analog video. This offers a much higher resolution and much higher frame rate of video than is possible with analog. And that image quality remains really good even in the presence of a bit of interference, because if there are packets of data that are being lost, then they're being retransmitted and that data is being recovered. And that allows you to really maintain an excellent image quality even as you fly far away or fly behind objects. A disadvantage of DJI's compression approach is that it requires whole frames of video in order to work, which means that the video transmitter has to wait for a whole frame of video to be received from the camera before it can encode it and transmit it, and this increases latency. Now, DJI have compensated for this by using a high frame rate camera and a high-speed MIPI link to the VTX, and that allows them to get that whole frame of video more quickly. But all of this adds cost to the system, and so that's going to make it more expensive than an analog system, for example. Another disadvantage is because all the data for a frame of video is required to reconstruct it, any lost packets have to be retransmitted, and this adds a variable amount of latency depending on the interference, and that can make it difficult when you're flying very, very fast in close proximity. And that's why racers still prefer analog video, because the latency is consistent and therefore it's more predictable when you're flying fast and close to objects. I hope you enjoyed that deep dive into the DJI FPV system, and that now you feel like you know a little bit more about how the system works and the advantages and disadvantages it has compared to analog. In my next video, I'm going to be doing a similar deep dive on the HD0 or SharkBite digital video system. So make sure you're subscribed and hit the notification bell so you don't miss that one. If you liked my work and would like to support me, and you're interested in getting some sneak peeks of the projects that I'm working on and access to my Discord server, I'll put a link to my Patreon down in the video description. You can join for the price of a coffee or a beer and get access to all those goodies. That's all I have for you for today, so until next time, I wish you all very, very happy flying.